Hello and welcome to the next edition of the Briefings Direct Voice of the Customer podcast series. I'm Dana Gardner, Principal Analyst at Inter Arbor Solutions, your host and moderator for this ongoing discussion on digital transformation success stories. Our next extreme use case for high-performance computing examines how the strictly governed redesign of Formula One race cars relies on data center innovation to coax out the best in fluid dynamics innovation. We'll now hear how Alfa Romeo Racing, newly named from Alfa Romeo Sauber F1 team in Hinwil, Switzerland, leverages the latest in IT to bring hard-to-find but momentous design improvements from simulation to wind tunnel to test track and ultimately to victory. The goal? To produce cars that are glued to the asphalt as well as sliced through the air. Here to describe the challenges and solutions from the compute-intensive design of Formula One cars is Francesco Del Cito, Head of Computational Fluid Dynamics Methodology for Alfa Romeo Racing in Switzerland. Welcome, Francesco.
Hello, welcome.
We're also here with Peter Widmer. He's Worldwide Category Manager for Moonshot, Edgeline, and IoT at Hewlett-Packard Enterprise. Welcome, Peter.
Welcome.
We're glad to have you both with us. Tell us a bit about why the Alfa Romeo F1 team, what they need to do to prepare for a new car design. Why is this a large undertaking when you're only moving from one type of iteration onto the next?
Effectively, it's a continuous design process, so we never stop, especially on the aerodynamic side. And what we do to design the car, what every Formula One team does, it's dictated by the season and by the planning and so what you want to bring in terms of performance or your concept of your car. Especially for Formula One racing, one of the most important, if not the most important discriminating factor in terms of performance is aerodynamics. And we, any Formula One team is putting a lot of efforts in designing the aerodynamic shape of the car, which includes cooling, brake cooling, engine cooling, and everything else. So all the flow, the airflow that is around and inside the car is simulated. It has to be controlled, it has to be simulated to try and extract the maximum performance.
And so this is as much an engineering competition as it is a racing competition.
It's both, actually it's both. So on track it's clearly a racing competition between drivers and teams, but before you get to the track it is an engineering competition in which the engineers, they both design the cars and they design the methods that they use to design the cars. Because each Formula One team has its own methodology developed, its own process, and they are kind of unique.
So when I first heard this, using fluid dynamics and aerodynamic optimization, I was thinking about reduction of friction. But this is also about making the car press down, using the aerodynamics like a reverse airplane wing. And you're reusing the airflow for things like cooling and other things. So tell us why the aerodynamics is much more complicated than people might have appreciated.
It is very complicated. Actually, most of the lap time that you can gain you don't gain it on the straight, so where you reduce the friction, but you gain them in the corners. If you can increase the amount of force that the air is acting on the car to push the car down on the ground, this is, let's say, a free force. Because if you add weight to the car, you have more force that is pushing the car down, but you have more inertial force, which is pushing the car out of the line, of the racing line. While with air, this is a sort of free because it doesn't come with extra weight, so with the extra inertial forces. But at the same time, it's difficult to generate it in an efficient way, so without it penalizing too much the friction. It's difficult to generate it without breaking the rules, because there are rules, there are limits, and there are for designing the shapes of the car. You cannot do whatever you want. And within these rules, you have to try to extract the maximum. And the force that the car is generating down, what we call downforce, which is, as you say, is the opposite of an airplane. The airplane is designed to just lift in the air. The racing car is designed to be pushed on the ground. The more you can push on the ground, the more you have grip between the tires and the asphalt, and the more you can go fast in the corner before the friction gives up and you just take start.
And how fast do these cars go nowadays?
Actually, they are fast on the straights. They are around 360, 370 kilometers an hour. In miles an hour, I don't know, but they are quite fast, especially in Mexico City, where the air is thin, so you have less resistance, and they have a very long straight. This is where you get the maximum speeds. And in Monza, which is a quite special circuit, for which every team designed a special aerodynamic package to reduce the friction, because in that case, this is rewarding in terms of lap time. But for what is impressive is the corner speed. In a corner, you can have, let's say, at the side acceleration, 4 to 5 times the acceleration of gravity. And it's like in a jet fighter, more or less. So it's really, really, really high.
Somebody told me that they're wearing the security belts, not only to hold them in case of an accident, but as well in terms of when they brake. Otherwise, they will be catapulted out of the car during the brake forces, which are kind of close to 5G. So the efficiency of the car is really the impressive stuff, not only the acceleration or high speed. So the other invisible forces which differentiate a Formula One car from a normal street car.
And Peter, because this is an engineering competition, before we get to the racetrack, doing those simulations, making sure that you can get minor but very impactful improvement falls back to the data center and its innovation. So tell us why a high-performance computing environment is an essential part of the overall team for producing these Formula One cars.
As Francesco already explained, it's as well a constructor or engineering competition. So to find the tenths of a second on the racetrack where a lap time can be 1 minute or more, that really brings the development of the cars to the edge. And to find the right solution requires as well some compute-aided design guidance or help. And that's where the data center can play its important part. So the simulation will take place at the data center, so CFD. So that's why we are so happy to work together with Sauber and to act as a technology partner.
And Francesco, when we do these simulations, are you able to have unlimited compute capability, or do you have constraints on what you can do with the computers as well as what you can do with the cars?
Yeah, I would like to, but no, I can't. So there are limits for the aspect of the car design, and especially in aerodynamic research, because the aerodynamics is where you can extract more performance, but is where you can spend more money as well. So the governing body, the FIA, a few years ago started to put in place some indirect ways of controlling the money spent for aero research. So instead of putting a budget cap, they decided to put a limit on the resources you can use. The resources are both wind tunnel and so experimental side wind tunnel and computational fluid dynamics. And it's a trade-off between the two. So the more wind tunnel you do, the less computational power you can use, and vice versa. So each team has its sweet point depending on the strategy, but in any case you cannot run unlimited. You have restrictions in how much computational capacity you can use to solve your simulations. You can do post-processing, you can do pre-processing in almost a limited way, but you cannot extract too much from there. The solving part, which is what it tells you the results of a new car design on the performance of the car, is what it is limited, and it's not unlimited.
Peter, how does that translate into an HPC and HPE equation? How do you continuously innovate to get new ideas in how to extract the most from the data center, but without breaking the rules?
I think the most important here is that we work with a competency center on HPC, which runs, I don't know how many benchmarks they run and tests they run to figure out the right combination of CPU, throughput, and the result on which is limited by the regulations. So basically, we were very open on the platform that we would suggest to Sauber or to other teams. And based on the most efficient combination of CPU, memory, networking, that was the final decision to offer that for the CFD use case. So it's know-how about how to tune CPUs, about the use case of CFD itself, and the knowledge on the regulation formula, which then leads us to get that success in CFD in Formula One.
And let's hear more about that recipe for success. What is the processor? What's the server? What kind of memory? And what kind of a rack configuration?
It's Skylake CPU. From Intel, of course, yes. The speciality on that CPU is that CPU includes graphic cards on board, which obviously is not used for the CFD use case. But the memory, we can use it as a level 4 memory cache, which then gives us the extra performance, which is not coming from the CPU, which is regulated. And due to the high packaging of the Moonshot solution, where we can put 45 compute nodes in a 4.3U rack chassis, that made us offering a quite compact solution. And we just talked about this, about 5,000 plus cores.
Yeah, the 5,760, I think, cores. And as Peter was saying before, the key factor here is the software as well that you use. Because there are, I would say, three main CFD software used by all the Formula One teams. There are many more around, but the Formula One teams, there are three main ones. The main limitation is always, for this kind of software, it's always the memory bandwidth. It's not the computational power, it's not the clock frequency. The main limitation is the memory bandwidth. And this is why the 4-level cache is giving this extra performance, even compared to the most, let's say, higher spec of Intel server CPUs. This lower spec, if you can say like that, this low energy version is giving us the extra performance because of this extra cache.
And this isn't some sort of workload you can get off of a public cloud for timeshare. You need to have this close by on premises because you're doing thousands of simulations. Isn't that right?
This is right. We're doing the server, the HPC facility is completely owned by us and run by us only by the Formula One team. Not only for aero research, but even for customer jobs or for track analysis data as well. So we use it for multiple purposes, but it's fully dedicated to the team. And it's not in the cloud, it's in the wind tunnel building actually, where we have a lot of electricity and cooling capacity. Consider that the wind tunnel fan, only the fan is using 3 megawatts. So we have a lot of electricity there.
So we're actually using the wind tunnel to cool the data center.
Sort of. We use the same water we use to cool the wind tunnel. But the wind tunnel has to be cooled as well, because you need air always at a constant temperatures to have consistent tests.
Peter, this configuration that HPE has put together that is perfectly tuned and designed for Formula One fluid dynamics simulations and other compute tests, this isn't just a one-off. You're doing this for many other Formula One car companies and backers as well.
Yeah, obviously the solution and the fit for the regulation was so compelling that we managed to get 6 out of 10 teams to use that platform. So some of them are heading the competition. So basically we can say that at least the first 3 teams are on our customer list. So maybe the other ones which didn't succeed that season come back to us as well, but who knows? But yes, we are very proud of that. We can deliver that platform to a sport which is known as heavy competitive, very technology oriented, and it's not comparable to any kind of other sport where you consistently evolve and develop and build new stuff. So it's the evolution is never stopping in Formula One. So it's for a vendor like HPE, it's really a very nice environment where if you have a new idea which gives a team a small competitive advantage, they don't say to you, oh no, we do that for 10 years now. Maybe I know. So they just say, okay, let's figure out how faster we can go, and then let's go for it. So they are literally open-minded to new solutions, and they are eager to learn about what's coming down the street in technology and could we get some benefits out of it. So that's really the nice story around it.
Francesco, as you mentioned at the beginning, this is a continuous journey. You're always looking for new improvements. You're always redesigning. So now that you've got a very sophisticated high-performance compute environment for doing fluid dynamics and simulations, what about taking advantage of HPC for data analysis, for getting closer to what people call artificial intelligence, machine learning? Is this the next stage in where you go with these very powerful applications? Do you start to combine that now with the data analysis to push the needle even further?
This is, let's say, we generate tons of data, both from experiments, so from the wind tunnel, from the CFD side, the computation fluid dynamics, and from the track. So we have a lot of data. The car is full of sensors. During Friday practice, there are hundreds of pressure sensors around the car. In the wind tunnel, there are like 600, 700 sensors constantly running. So as you can imagine, we have accumulated a lot of data. Now the natural step will be how we can use them. Yes, this is something obviously everyone is considering, and I don't know where this will bring. But yeah, there is nothing else I can comment on this at the moment.
It'll be interesting because if they have to put rules around the extent to which you can use a data center, they're probably going to have to put rules around the extent to which you can use artificial intelligence. So it'll be another level of rules, but it could still be very powerful.
It could be very powerful. Yeah, you are suggesting something to the rule makers now. Obviously, we have to work with what we have now and see what will come next, and we don't know yet. But this is something we are keeping our eyes open.
Well, good luck on your redesign and your next season of Formula One racing.
Thanks a lot.
I'm afraid we'll have to leave it there. We've been exploring how the strictly governed redesign of Formula One race cars relies on data center innovation to coax out the best in fluid dynamics innovation. And we've learned how the latest in HPC brings about small but momentous design improvements, from simulation to wind tunnel to test track and then ultimately on to victory for the Alfa Romeo Sauber Formula One team. So please join me in thanking our guests. We've been here with Francesco Del Cito, head of CFD methodology for the race team based in Zurich. Thank you.
Thank you very much.
We've also been here with Peter Widmer, worldwide category manager for Moonshot, Edgeline, and IoT at Hewlett-Packard Enterprise. Thank you, Peter.
Thanks a lot.
And a big thank you as well to our audience for joining us for this Briefings Direct Voice of the Customer Digital Transformation Success Story. I'm Dana Gardner, Principal Analyst at Inter Arbor Solutions, your host for this ongoing series of Hewlett-Packard Enterprise-sponsored interviews. Thanks again for listening. Please pass this on to your IT community and do come back next time.